So we're gonna go over section 14.2. This is double integrals and volumes. I'm gonna go over some of the examples that I found interesting in this section. Number 9 is the first one that I will be going over. Here. So number 9 is asking iterated integrals with the surface, sketch the region R and evaluate. The region R for number 9. So they give us the two bounds for the integral, double integral. And it's from negative a to a. And then negative root a squared minus x squared. And a squared minus x squared. And the function we're integrating over is x, y. And we give it in the order dy, dx. Alright, so ready?
Yeah.
Alright. So the next thing we got to do is it's asking to sketch the region. So we're going to sketch the region with the bounds given on the integral. So for the x, it's from negative a to a. And for the y's, it goes from positive root a squared minus x root x squared, and then the bottom part the negative. So this is the root a squared minus x squared, and this is the negative side of the semicircle, x squared. Alright, so the most important part is getting the region and knowing what it looks like, which they give us here. So then we just go ahead and straight integrate with respect to y first. So then we get xy plus y squared over 2, and the bounds negative a squared minus x squared, and a squared minus x squared. And this is dx, negative a and a. And then once you distribute these two in here, then I got x root a squared minus x squared plus a squared minus x squared over 2 minus x a squared minus x squared plus root a squared minus x squared over 2. So then some of these cancel out, and I got left with the integral negative a of 2x a squared minus x squared, and we're just left with respect to dx, which is the second order of the integral, and this is a u substitution. Once I did the u substitution, I got 2/3 a squared minus x squared, 3, 2, with negative a and a. And once I calculated that, then I came up with 0 once I distributed. So that completes number 9.
Yeah.
Alright, so there was a slight typo right here. There's no square root on this one. Once you put it into the integral with the square, then the square root gets rid of it. So these two cancel because the negative gets distributed to the positive. This one's already positive, so this one cancels on with this one. And then this one goes in here, so it turns positive. So we got one of these and one of these. So we end up with 2 of these. And then after that, we do the u sub.
Yeah.
Alright, so the next problem I'm going to be doing is number 11. Also from section 14.2. Number 11 is asking set up integrals for both orders of integration. Use more convenient order to evaluate the integral over the region R. Okay, so the problem is set up double integral, region x, y, dA, and the region is a rectangle, okay, with vertices 0, 0, 0, 5, 3, 5, and 3, 0. So we're going to go ahead and sketch that region. Okay, x, y. Alright. So this is the region we're interested in. It's going to be 3, 5. And this is 3, 0. Okay. So it's asking for both directions. So this is a rectangle. With the rectangle, it doesn't really matter which direction you choose too much. but we're still going to set them up because that's what the question asks us to do. So we're going to first do with respect to dy dx. Okay, so dy dx. So in the y direction, we go from 0 up to 5. So the bounds will be from 0 to 5. And in the x direction, we start at 0 and we go all the way to 3. So this goes from 0 to 3. And then this is x, y. So we go ahead and evaluate that with respect to y first. So then we get xy squared over 2, 0 to 5 dx. So we get 25 over 2 x, 0 to 3 dx. And then after that, we take the integral with respect to x. So then we get 25 x squared over 4, and then 0 to 3. And that gives us 225 over 4. So that was with respect dy dx order first. So now if we take the second order, which would be in the x first, and then the y. So same thing, we start with the x. So we do from 0 to 3. So we set up the integral, the bound from 0 to 3. And then the bound to y, being the second one, 0 to 5. Same function, xy dx dy. So with respect to x first, we get x squared over 2 y 0 to 3. Plug in that. We get 9 over 2 y 0 to 5 dy. And then we were to get 9 over 4 y squared. And then 0 to 5. And we verify that the answer once again is 225 over 4. So there it is. Alright, so the next one we're doing is number 24. And number 24 is asking, use double integral to find the volume of the indicated solid. So they just give us a graph and what some of the bounds are. So this is going to be a 3D. And we got up to 4 on this one, on the Z. And then right here, we got the line. And then, alright, this one's 2. And this one, y equals x. And then this other bound is y equals 2. Okay, and then this comes down this way. And this one comes down this way. So in order to understand this problem a little easier, so we can use the double integrals to find what we're looking for, which is the volume, I would highly suggest to just get this bottom region right here, because this is the y and this is the x. So those are the two planes that we know for double integrals. So we can go ahead and redraw this on the x, y plane to make it more visible. So the bound was up to 2, and then this is the x, and this is also 2. Okay. So then with looking at the bounds, we set up our double integral. Now that we have it in 2D, it's easier to see the bounds compared to this 3D here, which is a little more difficult to see because of the z. So this is z right here. Z equals, this is also given in the problem, z equals 4 minus y squared. Okay, so this z component right here is what goes, that's what we're integrating over. So 4 minus y squared, and we are going to go and dy dx. Okay, so then the bound is going to be from x to 2 for the y, x, and this is 2. And then for the x direction, we're going to go from 0 to 2. So from 0 to 2. Okay, so now we got it set up, then we can just go ahead and take care of this problem. So 4y minus y cubed over 3, and then x squared, okay, 0 to 2, and then dx. And once we distribute that, then we get 8 minus 8 over 3 minus, and then 4x minus x cubed over 3. simplifies to 16 over 3 minus 4x plus x cubed over 3. And we still have the integral from 0 to 2 dx. Okay, so we did that, and then after that we take the integral with respect to x. So then we end up with 16 over 3x minus 2x squared, and this is plus 412. Okay, so x to the 4th over 12, and then that was from 0 to 2. Okay, and then once we distribute this right here, then we got 12 minus 8, and that equaled 4. So the volume of the region equaled 4 units cubed.